This presentation is on internal migration, or stoping. The purpose of the presentation is to explain the internal erosion process of internal migration and explain situations where open defects in foundations, conduits, drains, or unfiltered exits in embankments may occur. We'll start this presentation with an overview of the internal erosion process and then discuss internal migration into open defects in foundations, conduits, and drains. First, an overview of the internal erosion process. Internal migration occurs when soil particles move or drop into an open defect. Soil particles that drop into the bottom of the void are carried away by seepage to an unfiltered exit. If extensive void space exists in coarse soils or bedrock, an open exit may not be needed, but sufficient storage space for eroded fine particles must be available. The process is repeated progressively, causing the void to enlarge and migrate vertically upward. Failure from internal migration can occur if the sinkhole is large enough to cause overtopping, if the core is breached by the sinkhole, or the downstream or landside slope of the embankment is oversteepened to the point of instability. Internal migration can also occur if there are open joints or defects in conduits, drains, or other structures that are not filtered, or if there are untreated rock defects in the foundation. The voids or sinkholes can form upstream within the central portion of the dam or on the downstream shell. The most critical location for a void to form is beneath the impounded water, as this leads to potential introduction of full hydraulic head to a more downstream location. Internal migration into rock defects is the most common scenario for USACE dams, whereas internal migration into defects in conduits is the most common scenario for USACE levees. Some other things to consider for internal migration are this failure mode can develop very slowly over a long period of time. It can be very difficult to detect until the void progresses to the surface and is observable, and successful intervention is likely if the void forms above the water or on the downstream slope. Our first scenario of internal migration into open defects in conduits or drains will be discussed in the following slides. Here's the event tree for evaluating internal migration into conduits, pipes, or culverts. Node 1 is the flaw node. It's an open defect that exists in the conduit or pipe, etc. Node 2 is initiation. We need a downward gradient to initiate internal migration. There also has to be enough water flow in the pipe to transport the eroded particles downstream. Node 3 is continuation. An unfiltered exit exists that allows erosion to continue. Node 4 is progression. The leakage fails to clog and a stope develops. The common progression node of holding a roof applies to concentrated leak erosion, and it's not evaluated for this internal erosion process. Node 5 is intervention. Detection and intervention are unsuccessful. And then finally, node 6 is breach. Uncontrolled release of impounded water occurs. As water is impounded, a phreatic line develops and seepage forces are active in saturated soils around the conduit. Seepage can enter any defects into the conduit if the conduit has an interior pressure lower than the water in the soil pores. If seepage discharging into a non-pressurized conduit has sufficient gradient and the soils are erodible, soil particles may be carried with flow. Internal migration will cause a void or a sinkhole to develop. Defects in conduits can be caused by embankment settlement, which can lead to lateral spreading and subsequent opening of joints. Differential settlement can also cause joints to open. On the left, we can see water seeping through a joint in an outlet works conduit. The joint has experienced differential settlement. It has no longitudinal reinforcement extending across the joint, and the mortar joint filling had cracked and deteriorated over time. And then on the right, we have an example of soil particles that are being carried into an outlet works conduit through a joint. Joint offsets can cause high negative pressures to develop at overhangs during high velocity flow within the conduit from a Venturi effect. Negative pressures can pull or suck surrounding soils into the conduit through openings, and voids can develop adjacent to the conduit. A continued loss of surrounding soil could lead to the development of a sinkhole, which can then lead to breach if it were to connect to the reservoir. Conduits that get pressurized can force water into the surrounding earth fill. When the flow reduces, that water will seep back into the conduit, bringing soil particles with it. This process is cyclical and may take a long period of time to develop to the point that distress is observable. This slide shows a few different methods that we can use to prevent open defects from occurring. On the left, we have a control joint that's used in reinforced cast-in-place concrete conduit construction, with longitudinal reinforcement being continuous through the joint. And on the right, we have an example of a water stop that's placed across the joints of conduits to stop water from coming through the joint. On the top right, we have a typical water stop detail, and on the bottom right, we show a typical water stop that we use in conduit construction. For constricted exits, progression is limited due to the erosion resistance of the structure, concrete or metal. The likelihood of continuation can be determined using the constricted exit worksheet in the RMC Filter Evaluation Continuation Toolbox, and the criteria for that evaluation is provided in the continuation presentation. Pine Creek Dam is a case history of erosion into the conduit. Soft areas with low blow counts and a large void were found above the conduit, and the figure shows the location of the soft zones in red and the large void in green. The photo on the right shows leakage that was occurring into the conduit. The project was remediated with a cutoff wall above the conduit, a drilled-in chimney filter, a downstream conduit perimeter filter, and a new steel conduit liner. This table from the Best Practices Manual can be used to help assess the likelihood of open defects in conduits. It can be used as a starting point, but the risk team must develop project-specific more likely and less likely factors to guide subjective probability estimation. The factors in this portion of the table address sinkholes or depressions in the embankment over the conduit alignment, conduit joints or cracks, hydraulic operation and control, connections to other structures, conduit type, and conduit corrosion. Internal migration can also occur due to erosion into drains that are damaged or not properly sized as filters. These can include relief wells, toe drain pipes, rock-fill toe drains, and stilling basin under drains. Drain pipes should all be inspected. Video inspection of pipes or drains is essential to assessing the likelihood of having an open defect. Corrosion of metal pipes creates holes that become unfiltered exits. The photo on the right is an example of a corroded corrugated metal pipe at Herbert Hoover Dike. If you don't have information from a recent inspection, the RMC Pipe Service Life Flaw Toolbox can be used to evaluate pipes with respect to having a defect, such as a perforation, serious degradation, etc., that is present that can help assess internal migration through a defect. This tool should only be used when the existing condition of the pipe is not known from a recent inspection within the last 5 years or so, particularly with respect to the culvert's invert. There is also some additional information in the new EM 1110-2-2902 conduits, pipes, and culverts associated with dams and levees. This table from the Best Practices Manual can be used to help assess the likelihood of open defects in conduits, pipes, culverts, or drains. It can be used as a starting point, but the risk team must develop project-specific more likely and less likely factors to guide subjective probability estimation. The factors in this portion of the table address material transport, presence of seepage, presence of open cracks or joints, pipe characteristics, and filter and drain envelope considerations. The factors in this portion of the table address sinkholes or depressions, structure under drains, inspections, voids below or adjacent to the pipe, and the location of tow drains. Next, we'll discuss internal migration into defects in the foundation. Here's the event tree for evaluating internal migration into rock defects in the foundation. Node 1 is the first flaw node. An open rock defect exists in contact with the embankment that has sufficient void space or that daylights downstream. Node 2 is a second flaw node. The foundation treatment is ineffective. Node 3 is initiation. A downward gradient exists to initiate internal migration into the defect. If the exit daylights downstream, there also needs to be sufficient gradient to transport the particles to the exit. Node 4 is continuation. An unfiltered exit exists. Node 5 is progression. The leakage pathway fails to clog. Node 6 is intervention. Detection and intervention are unsuccessful. And finally, Node 7 is breach. An uncontrolled release of impounded water occurs. One way rock defects are commonly formed in river valleys is due to stress relief. Erosion that forms the valley relieves the in situ ground stresses in the vicinity, causing passive failure and results in the formation of joints. This is very common in sandstone or shale geology. Vertical joints are typically oriented along the valley walls, thus creating upstream to downstream seepage pathways. A good example of valley stress relief is East Branch Dam. There was major stoping into the foundation that occurred in 1957. This case history is going to be discussed in a separate presentation, but the volume of the resulting void was the size of a school bus. Another mechanism for the formation of rock defects is karst, where defects are created by solutioning of the rock. This is an example from a rock quarry in Indiana. An example of this scenario is Freeman Dam, located in Elizabethtown in central Kentucky. Although the dam did not breach, the case clearly shows progression of a potential failure mode. The dam was a 50-foot tall clay embankment with a cutoff trench and tow drains, and it was built in the mid-1960s. Significant seepage issues were not reported until March 1997 following a record pool. Increased drain flows, seeps, boils, and saturated areas were observed downstream of the dam. Following an extensive investigation of seepage issues, a chemical grouting program was initiated in the spring of 1998, and during that grouting program, a void was encountered within the cutoff trench that extended up 11 feet into the core from the top of rock. The volume of this void was approximately 135 cubic feet. The dam was breached and the foundation was exposed, which revealed solution features present beneath the embankment. Clearly, the infilled soil in the solution features had eroded over time, providing an open conduit for seepage to carry off the core material. It was noted that no dam or foundation soils were ever observed on the surface or downstream of the dam. Foundation conditions revealed in excavations led to a decision to completely remove and rebuild the dam with proper cutoffs, rock treatment, and filters. Imagine water coming up during a high pool event, unraveling some of the overlying clay core, and removing soil particles as the water level receded. These karst features did not daylight at the downstream tow, and therefore no dirty water was ever observed at the site. This map shows areas where certain rock types that are susceptible to dissolution in water occur. These rock types are evaporites, such as salt, gypsum, and anhydrite, and carbonites, limestone and dolomite. Evaporite rocks underlie about 35 to 40% of the United States, though in many areas these rocks are buried at great depths. Here we show a simple cartoon for the process of how karst forms. As rainwater passes through the atmosphere and the soil, it picks up carbon dioxide, which dissolves in the water to form weak carbonic acid solution. This acid then seeps into the rocks and dissolves the calcium carbonate limestone. Structure is important for karst development, and karst is opportunistic. water flows along pre-existing cracks, faults, joints, bedding planes, etc. And dissolution is normally worse near the surface. As water works deeper, its calcite concentration goes up and it becomes less aggressive. Rock foundations that consist of evaporite rocks, like gypsum, are potentially more problematic than limestone simply due to the rate of dissolution. Mosul Dam in Iraq is a good example where grouting has been ongoing since the dam's completion to treat the continuous deterioration of the foundation. Here's a map of USACE structures that are located within karst regions. 25% of USACE structures are mapped in carbonate regions. Here are some key considerations when evaluating karst. Karst initially develops along joints, faults, or bedding planes. Groundwater and environmental conditions that formed the karst may no longer be present, and subsurface groundwater flow directions may be unrelated to surface water flow direction. Karst can be open or infilled. Karst infilling can have different sources, such as alluvial, glacial, residual, organic, or junk. Infilled soil in karst may have very low confining pressures, and the voids in karst are likely interconnected since they were formed by drainage. The three primary issues with karst are excessive leakage of reservoir water, transmission of high pore pressures to downstream foundation, and internal migration into a void or concentrated leak erosion along the soil void contact that leads to sinkhole development and collapse or connection to the pool. When evaluating the first node of the event tree, consider the following factors. Is the geological environment likely to have open or infilled continuous features? What is the topography of the dam site? What's the steepness and what's the valley depth? What is the continuity and orientation of the defects from surface mapping of the abutments? Is there blast-induced damage to the rock formation for dam cutoff or conduit trench that can also lead to open defects? Construction photographs and mapping are often the best guide as to whether such features may exist and their likely continuity and opening. Don't consider cutoff elements at this point in the event tree. Effectiveness of foundation treatment is a separate node. This table from the Best Practices Manual can be used to help assess the likelihood of open defects in the foundation. Generally, open defects in the foundation are associated with rock formations. However, open-work gravel foundations pose similar issues for internal migration as well as soil contact erosion. This table can be used as a starting point just as with the other tables, but the risk team must develop project-specific more likely and less likely factors to guide subjective probability estimation. Node 2 of the event tree evaluates the effectiveness of any foundation treatment. Effective foundation treatment isolates the embankment from the foundation and its open defects. Assess the effectiveness of dental concrete, foundation shaping, removal of fractured rock blocks and overhangs, air or hand cleaning, slush grouting, concrete bulkheads, filters at the embankment foundation interface, seepage barrier or cutoff elements, etc. Be wary of a reliance on grouting to serve as the sole design feature to control seepage. And consider information in the foundation report, construction photos, geologic mapping, as-built drawings, performance, and instrumentation. This portion of the table from best practices can be used to help assess the likelihood of foundation surface treatment and foundation grouting not being effective. These tables can be used to help assess the likelihood of grouting or cutoff walls not being effective. The factors for grouting address orientation of the grout holes compared to the open defects, quality of the grouting, and performance in relation to pore pressures and leakage. The factors for cutoff walls include width and depth of the cutoff relative to the defects, performance in relation to pore pressure and leakage, and quality of the cutoff. These tables can be used as a starting point, but the team must develop project-specific more likely and less likely factors to guide subjective probability estimation. For sinkholes to develop, a downward vertical gradient into the rock foundation is needed. Evaluate piezometers and seepage analysis to show patterns of what could happen if rock voids are present beneath the dam. Pore pressures are very low on the downstream side because a solution feature is acting like a drain. So lowering of piezometers can be an indication of karst drainage. This slide summarizes the conditions for sinkhole development. The conditions for the formation of a sinkhole include open voids or slot in rock formations large enough to develop initial soil voids at the soil-rock interface. Next, we have flow in the rock mass that is sufficient to wash away collapsed soil so that the void can enlarge. We have downward seepage flow gradients across the void roof that will cause raveling of the soil void roof and cause the stope to progress. Now, some things that can accelerate sinkhole formation include lowering of the groundwater table below the void roof, an increase in downward hydraulic gradient, cyclic rise and fall of groundwater above and below the roof of the void, and surges from changes in tailwater elevation. Here are a few examples of sinkholes on or near dams. In the left, we have Center Hill Dam. In the early 1990s, seepage through the left abutment rim dramatically increased, including discharge of very large volumes of soil, 5,000 cubic yards, into the downstream channel. This was followed by the development of numerous sinkholes in the left abutment. In the middle, on the top, we have an NRCS dam where a sinkhole manifested at the ground surface. The middle bottom, we have Wolf Creek Dam. After 17 years of operation in 1968, sinkholes developed near the switchyard at the downstream toe. And then finally on the right, we have Clearwater Dam. A sinkhole appeared on the upstream slope above the pool following a record pool. It's believed that the sinkhole developed below dental treatment through a karst feature that was originally soil filled but over time was cleaned out by erosion. Here are some observations made from sinkholes on dams. The process appears to be cyclical, related to the rise and fall of the reservoir or tailwater. Most sinkholes were cover collapse type of sinkholes near the crest or on the downstream side of the embankments. This may be related to where the gradient direction becomes downward in the dam foundation. Collapses have been sudden, without superficial signs, and muddy flows are only sometimes associated with sinkholes. The biggest thing is that sinkholes rarely lead to failure due to successful intervention. To summarize this mechanism, this slide presents an example from the Mosul Dam risk assessment of a sequence of events that would need to happen to lead to failure. A continuous network of interconnected fractures and voids are present within Main Valley Dam foundation. Treatment of the foundation during and after construction was ineffective in cutting off or isolating the embankment core from the underlying defects. Erosion of the overlying soil initiates into open rock features below, and a void begins to form in the embankment core. The network of defects and interconnected voids through the foundation are sufficiently open, and seepage passes through these features with sufficient energy and velocity to continually transport eroded soil. The eroded core material is either transported to a daylighting downstream exit or is accepted by interconnected void space of foundation rock. The erosion continues and progresses as upstream zones fail to choke off a stope development, and the void enlarges and manifests as a sinkhole that reaches the reservoir. Detection and intervention are unsuccessful, and erosion and material transport continue and enlarges the sinkhole until crest collapse occurs, breaching the dam. To wrap up, we have a few slides on internal migration into unfiltered exits within the embankment. Stoping can occur in narrow or even reasonably wide sloping or partially sloping central core dams that are constructed with broadly graded cohesionless soils that are susceptible to internal instability if they're not properly protected by filters or a transition zone. Voids develop at the interface with the unfiltered exit that grow or stope upward and backward subvertically as erosion continues. Global backward erosion, GBE, is used by some organizations outside of the US, but the Corps considers this process to be internal migration. BC Hydro's WAC Bennett Dam in British Columbia is a case history of internal instability leading to stoping and sinkholes. This case history is discussed in more detail in the internal instability presentation. This concludes the presentation on internal migration or stoping.